Welcome everyone to the first colloquium of this fall season. And today I have the pleasure of introducing Ethan Vishniac, who is visiting us from the University of Saskatchewan. Ethan has enjoyed a long and successful career. He finished actually his PhD in 1980 at Harvard. Then he moved on to Princeton as a postdoc, where he worked with Jerry Osterreicher. And then he landed at the University of Texas in 1982 as a faculty. And after that, he's had many posts at different universities, namely Johns Hopkins in 1998, McMaster in 2007, and finally at Saskatchewan, where he's been for the last 2 years. And some of you may not know this, but he's also the editor-in-chief of a very well-respected journal, the Astrophysical Journal, AFJ, since 2006, so for the past 8 years. And when it comes to magnetic fields and astrophysical plasmas, Ethan is a well-renowned expert. In fact, there's an instability named after him, the Vishniac instability. And today he's going to tell us something about symmetry and the magnetic field.
Thank you. My mother hates that name, by the way. And I think after I moved to McMaster, or just before, I gave a talk here, and you pointed out that George Bush had been following me around and wondered if this was a harbinger of something really awful. But I seem to have broken that curse. OK, so I'm going to talk about basically dynamo theory. And being a theorist, I have only pictures and data that I've stolen from other people. I will try to give proper attribution, and don't ask me any deep, meaningful questions about these things. It's just meant to illustrate the theory, which, of course, is the underlying reality that we all aim for. So I was smiling when I said that. What is the problem that I'm concerned with here? Magnetic fields, as you all know, are found almost everywhere in the universe. Stars, planets, disks of galaxies, intracluster medium. They are typically organized on the scale of the system, which is to say that if you did a power spectrum of the magnetic field, there would be a significant amount of power on the size of whatever object they're embedded in. And the energy density is typically comparable to the energy density of the turbulence in whatever medium they're in. There's some wiggle room there, depending on non-local effects. They're responsible for particle acceleration in the universe, so indirectly for almost all of high-energy astrophysics. And in addition, they play, we think, a leading role in accretion, and therefore in star formation, radiation from black holes, other collapsed objects. So they're important. When I was a graduate student, almost the only place they weren't found was in the astrophysical literature, because they're notoriously hard to deal with. So here's another one of these pictures that I'm not responsible for. This is M51, our radio image. See the nice spiral pattern in the Whirlpool galaxy, and bright spot off to the side of the satellite galaxy. You can do a polarization map and superimpose it, and you see that the magnetic field has a similar spiral pattern. There's some ambiguity in maps like this because, of course, if you reverse the direction of the magnetic field, the polarization map would look just the same. So people have argued about to what extent a map like this shows a single overarching structure and to what extent there might be separate annular domains contained. Although it's a little hard to see how that could be true here. There are other cases where it's more ambiguous. So, there are two separate but important questions when you look at pictures like this. And the first one is how does the magnetic field get a large share of the energy in the system? Separate from how does it get organized. This is called the small-scale dynamo problem. I'm not going to say very much about that, just a few words. And then second, how does the power end up on such large scales? It's called the large-scale dynamo problem. It's an example of an inverse cascade problem where some kind of information or structure flows not down toward the smallest scales, what we're used to in turbulence, but up to the scales of the system. And it's not unique in that sense. There are other examples in geophysics, like hurricanes, for example, but it is somewhat unusual. Okay, so a few words about the small-scale dynamo. In a turbulent medium, it turns out that the magnetic field absorbs about 5% of the energy in the turbulent cascade in every eddy turnover time. And that doesn't actually depend on the scale of organization of the magnetic field. You may remember in ordinary turbulence, you have large-scale turbulent eddies, and the energy flows to smaller and smaller scales. Depending on the strength of the magnetic field, that energy will go to stretching out the magnetic field lines and pumping energy into the magnetic field, either on very small scales for a very weak magnetic field, or on larger scales as the magnetic field increases its energy. But regardless of where it's absorbing the energy in terms of scales, it's always about 5% per dynamical time.
There's less energy in small scale eddies.
It absorbs less in any given time, but it's cumulative. So I think that we supplied the first estimate of this number, but the best estimate is from Andrei Berezniak's simulations. So consequently, the magnetic energy density in the medium grows linearly. Now, in ordinary everyday language, we tend to think that exponential is fast and linear is slow. But in this case, if you imagine starting out with some infinitesimal magnetic field, exponential would be slow because it would take a very long time for enough E-foldings to go by. But linear means that regardless of the initial field strength, in about 20 eddy turnover times, the magnetic field is up to equipartition. And as it approaches equipartition, the scale of its organization reaches the scale of the large-scale eddies. Not exactly, but if you look at the power spectrum in simulations, you'll see the magnetic energy peak moves pretty close to the kinetic energy peak. I keep mentioning simulations because, of course, when we talk about magnetized turbulence, there's the unfortunate fact that our ordinary experience, even extraordinary experience in physical experiments, provides us very few examples of magnetized turbulence. And so the whole progress in this topic has had to wait until three-dimensional simulations of magnetized turbulence were possible. Okay. So there's a star nearby, and it's close enough that we can look at the details of its magnetic field. I don't know how well you can see this, but this is a picture of the sun in X-rays and an attempt to figure out where the magnetic field lines are popping up out of the surface and going back in, assuming a force-free configuration, and surface diagnostics of the magnetic field. And you see, a few bright, intense spots in X-rays where lots of magnetic field lines are emerging. So the overall picture here is a bit complicated. Here's a nice close-up in visible light of a sunspot. Looks very dark in here, right? That's because the black body emission goes as the fourth power of the temperature, and it's a frigid 4,000 degrees in the middle of that sunspot, so it's very dark compared to the rest of the surface. Those are the spots where intense bundles of field lines emerge from within the sun. And if we plot the sunspot number as a function of time and latitude, and we have records now going back not quite 150 years that we can use to reconstruct this, what you see is that the magnetic field lines emerge in these bundles at mid-latitudes, and then as time goes on, emerge closer and closer to the equator, and then the sun gets quiet for a little while and it starts the whole cycle over and over. The cycle length is not an extremely good clock, but it's not terrible either. It doesn't wander all around. And the intensity varies from one to another. We know also from observing this cycle that the dipole field of the sun, the poloidal field, reverses sign in every at the end of every 11 years during this quiet period. It's reestablishing itself. And so a complete cycle is really twice. It's 22 years till we're back to where we started. The typical dipole strengths on the order of tens of Gauss. The fields in the sunspots, which we believe are samples of the internal field of the sun, are kilogauss. And here you see a plot of sunspot number. Not very good statistics in the beginning. From their discovery by Galileo Galilei, who I recently found out it was the second most famous Galilei of his time. No joke, really true. And what you see is that there's this funny minimum, and the cycles vary. It's not a random variation. There's a lot of correlation from one peak to another, but it's certainly not uniform. The sun is a little bit brighter during intense periods, not very much, maybe raises the global temperature by 1/10 of a degree or so overall. And we're now in a stage of at least temporary decreasing strength of these cycles, so that the global temperature should be falling. Everything else being equal, which of course it's not.
What happened in 17? To the data collection.
To the data collection, it became much better.
Yeah.
And there's some institutional thing that happened at that point. I don't remember what it was.
Telescopes well predate that. So.
That's right. Someone started keeping accurate records. The significance of sunspots at first, besides spoiling our image of the sun as a perfect object, also showed that the sun was a rotating, in fact, differentially rotating object. So that was a very big deal at the beginning. But the sunspots per se were of only passing interest. People didn't catalog them systematically for a long time. So what can we learn from the sun about the large-scale dynamo? Well, the sun at least shows these cycles. These sunspots give us a measure of the strength of the internal field of the sun. The length of the cycle turns out to be difficult to get correct in models. It may have something to do with meridional circulation within the sun. That's the general supposition at any rate. If we look at different stars, we do see different lengths of cycles, and some stars that show chaotic cycles. Nowadays, we can reconstruct the rotational profile within the sun, and we see that it's not just that the surface, different elements of the surface are rotating at different speeds, but there's actually quite a lot of structure in the convective zone of the sun. The interior here, the data is consistent with more or less uniform rotation. I mean, there's something of a bump over here, but this is probably not statistically significant. And what we see is that the equator here is rotating a bit faster than average. The poles are going a lot slower. And there's a zone of fairly intense shear up until mid-latitudes, and then shear of opposite sign up here. So I'm not going to say anything more about this profile. I know that people work on it, why it is what it is, but that doesn't really matter for what I'm going to say. OK, so the picture, the cartoon picture that people draw in order to explain what the sun is doing, it's called the alpha-omega dynamo. This is a famous diagram of it because it's a nice diagram. This is not the first place that it was presented by any means. But the idea is you imagine you start with some nice poloidal field. Because there's differential rotation, the field lines get tangled up and twisted around more and more, generating toroidal field until it's extremely toroidal. And then, and this is the miracle of making a schematic rather than showing what actually happens, then we suddenly apply turbulence to it. And it's very special turbulence. It has a preferred handedness, so that it makes these azimuthal field lines into spirals, not turning randomly this way or that, but systematically being right-handed in parts of the sun and left-handed in others. And then if we imagine that the field lines all reconnect, so they reestablish a kind of average field strength, what we're left with is a bunch of loops. And because loops of different strength are sitting next to one another, we have a regenerated poloidal field from this. Okay. How many of you know what Helfand's law is? No one. Helfand's law is the rule invented by David Helfand that you should never show equations to astronomers. But unfortunately, you can't be a theorist without showing equations. So we need to show some equations now. Good.
Helfand showed equations in his classes.
He did. I don't know why he said that. It's just, but it's funny. So I quoted. So anyhow. Okay, that, given the nature of entropy, might well be true. Okay, so in a highly conducting fluid, like a plasma, with light charge carriers, it's a pretty good approximation to say that the Lorentz force on a single particle is 0. So the electric field is minus v cross b, where this is the local velocity of the fluid. And so then you can use the induction equation to write a closed form equation for the magnetic field. And we're off. This is a famous equation, and it has some unlikely and almost certainly completely wrong consequences, which is the subject of a lot of discussion. You can prove from this equation that if you have a fluid element, the magnetic flux that threads it never changes. It's called flux freezing. So if you make a magnetic field line increase in strength, it's because you've taken the fluid element and made a needle out of it so that the cross-sectional area is tiny. You can make the magnetic field shrink by flattening the fluid element into a pancake. But you cannot change the topology of the field. Well, this is grossly inconsistent with observations of magnetic fields in the vicinity of the sun. And if it were true, then, for example, the dipole flipping of the sun every 11 years would rely on resistive effects within the sun, which would give you a natural time scale. I forget whether it's 10 million or 100 million years. It's a very long time, much longer than 11 years. So it turns out, and I won't say much more about this, that a solution is that in a turbulent medium, you can show that infinitesimal resistive effects that only involve neighboring field lines leads to the field being able to drift freely through the turbulent medium, because small-scale reconnections plus a turbulent wandering of the field lines gives you essentially complete mobility of the field lines in about a dynamical eddy turnover time. So we talked about the theory of this, Alex Azarian and I, back in '99, and there's a Nature paper, Eink et al., where et al. Includes a bunch of people, including me and, well, a bunch of people at Hopkins, showing how this plays out in a high-precision simulation. So flux freezing is not true, which is good. But we can still use the equation as an approximation for the motion of the field lines as long as we add some sort of local averaging process which respects symmetries. I'll get back to the symmetries in a second. But let me say something about the averaging process. The traditional way to apply an averaging process, which long predates any discussion about turbulence and reconnection, is to divide the field up into a large-scale field and a small-scale field. So here I've used a capital B and a little b, which is a pretty conventional choice. And then if you have some large-scale motion, like differential rotation, you have a capital V and a little v. And then physically, the evolution of the field is it gets dragged around, it gets stretched. And then there's something mysterious that the turbulence does to the field here, the electric field due to individual eddies. So you need, in order for this not to be zero, you need some coherent effect which makes all the eddies give a systematic contribution. So your first thought on looking at something like that ought to be that V cross B should be approximately 0. Because in a turbulent medium, why should these things necessarily have anything to do with one another? So the way we calculate it, there's a long history of doing sort of half-assed things here, but the systematic and consensus method now is that you assume it's approximately 0. You check its time derivative, and you multiply by a correlation time of the turbulence. So if you set it to 0, in one eddy turnover time, what would it grow to? Implicitly, there may be higher order corrections that go in that, and I will assume we don't have to worry about them. Okay, so you have the dynamical equations for the small-scale magnetic field and for the small-scale velocity field, and you can do this, and you get something that's very messy, but basically it's non-zero only if you have some correlations built into the turbulence. So in words, we write V cross B, the negative of the magnetic field, called by tradition, which I don't really understand, the electromotive force. And that has a contribution from the current helicity, which is current dotted into magnetic field, minus kinetic helicity, which is velocity dotted into vorticity. And then there's a cross helicity term, correlation between V and B. Then there are drift terms, like if the magnetic field is buoyant, and dissipative terms. Neither of those help run the dynamo. These are the things that run the dynamo.
Well, buoyancy is related to the fact that the star has a surface.
Yes. I'm just saying buoyancy could be in there. If you have turbulence in a box, it's not in there. Okay, so what terms do we worry about and what terms do we throw out? The conventional approach is that we throw out cross helicity. There are various reasons for this. I'm not going to belabor them. Basically, it's not terribly conserved. That is, it's lost on small scales, and it doesn't give you a useful dynamo effect. Kinetic helicity, V dot omega, which you can expect to arise because, well, there's a bunch of ways it can arise, but they all have to do with the global environmental surrounding. It's not conserved, but it may be imposed by the environment, and traditionally we keep it. It expresses the tendency of fluid elements to do right or left-handed twists, one or the other. Current helicity is not a conserved quantity, but the vector potential dotted into the magnetic field is a conserved quantity. It's a basic symmetry of the equations. And the current helicity and the magnetic helicity are highly correlated for a suitable gauge choice. So the fact that the current helicity is not conserved, but is related to the magnetic helicity, leads to a magnetic field back reaction. If you accumulate magnetic helicity, it drives a current helicity, which drives an effect which can turn off the dynamo.
Is magnetic helicity conserved even with this infinitesimal field line wandering?
Yes.
Whoa.
It is a robustly conserved quantity, meaning that small-scale effects don't do much to it. It is much better conserved than, say, energy in turbulence. Let me digress for a second, because this is interesting. If you look at it dimensionally, magnetic helicity is like an energy density times a length scale. Okay? So if you take a given density of magnetic helicity and you put it into increasingly small-scale structures, you need more and more energy to do it. Conversely, if you put it into large-scale structures, it costs you less energy. If you have a very wide scale separation between your turbulent eddies and the dissipative scale, you lack the necessary energy to do anything to that magnetic helicity. It's stuck up on the eddy scale. Very little of it is ever at the dissipation scale. So it is robustly conserved. And in the laboratory, in systems that dissipate energy quite quickly, the observed time scale for the dissipation of magnetic helicity is much, much longer. Yes, exactly. So traditionally, I would say this term is pretty much ignored, despite its connections to symmetries. It is either dropped or it's taken as an effect which can lead to suppression of the dynamo when the field becomes strong. Okay, so kinetic helicity, dot product of velocity and vorticity. What does it take for it to be non-zero in a given environment? The environment has to distinguish between all up and down, in and out, right and left, all of these things. Each reversal has to have a broken symmetry. So for example, differential rotation breaks symmetry in two directions, azimuthal and radial, but then you need the environment to supply the third amount of symmetry breaking, so the size of the box comes into it. So in the end, dimensionally, it's like v squared over some length scale. Because the size of the box has to come into it, that goes in the denominator. Because rotation or differential rotation has to come into it, we have something like that, where this is an eddy correlation time, and this is either the shear or the rotation or something multiplying it. And if you take all this seriously, you get an exponential growth of magnetic fields with a typical time scale which goes as the shear to the 1/2 power and this kinetic helicity to the 1/2 power. And it comes out to be like the size of the eddies over the size of the system times rotation rate or the shear rate or some geometric mean of the two. And this is what's called the kinematic dynamo. You're basically treating the magnetic field as though it's totally passive. So people have constructed models in which the field grows exponentially at this rate until it is obviously no longer passive, and that's taken to be the saturation of the dynamo. Now, for the sun, you have this region of very strong shear at the bottom of the convection zone. Omega times tau c, or S times tau c, well, omega times tau c is about 1 at the bottom of the convection zone. So one way or another, with some varying role by the convection and the tachocline, what's going on in the sun is apparently, in this model, driven by the base of the convection zone. And then in order to explain the solar dynamo, people have to put in other ingredients. Something to model the saturation of the effect, buoyant losses, back reaction from the large-scale field, put in the detailed rotational profile, and so on. You have to model the kinetic helicity, which is, in the jargon of the field, that's modeling alpha. Astronomers only know 2 or 3 Greek letters. Alpha is the one that works here. The alpha effect is the electromotive force that's proportional to the magnetic field. So you model that in some hopefully not too hokey way. And if you do everything, you can produce something that looks very much like the behavior of the actual solar magnetic field. Okay. Honestly, there are a lot of tunable parameters in these models that are not fixed by what we know about the sun. So getting something that looks like a solar cycle is kind of, well, it's physically dubious. There's a simple way to show that you can get a very good model even if all the physics is wrong. You can ask people to work with the incorrect physics and see what answer they come up with. And in fact, people used to do this until we knew the rotational profile of the sun. People produced pretty good dynamo models with the wrong rotational profile. So this is, okay, maybe it's not a cause for despair exactly, but it's not a great triumph. It's not unique. There's not a unique connection between fundamental physics and what the dynamos models do. But then in modern times, we've also discovered that this approach does not give a good match to the simulations of stellar dynamos either. Of course, numerical simulations have their own problems, but they generally don't show a good correlation between the electromotive force and the kinetic helicity. There is a theoretical objection to the whole program called alpha suppression, which is now about 20 years old. Basically, it's that the current helicity that appears naturally in the course of the evolution of these systems becomes large long before the field is large and turns off the alpha effect. So let me say a word about where this comes from. Okay. Magnetic helicity, A dot B, is a conserved topological quantity that is a measure of the twistiness of the field.
It's integral.
No, I mean, let me say something about that. The magnetic helicity locally is gauge dependent. The integral over a volume is not gauge dependent. The non-gauge dependent quantity is, of course, the current helicity. So you have an infinite family of conserved quantities depending on your gauge choice. But only a small fraction of them correlate the magnetic helicity locally with the current helicity. And the Coulomb gauge is computationally tractable and does that correlation. So I'm going to use the Coulomb gauge and everything that happens from here on and use that as a unique definition of A dot B. Regardless of gauge choice, this is a conserved quantity. And it is useful to separate out the contribution from the large scale twisting of the field and the eddy scale twisting of the field. You can write these as a capital H for large scale and little h for small scale. Little h is the correlated magnetic helicity over lots of eddies, but it's always the fluctuating vector potential dotted into the fluctuating magnetic field.
You were saying earlier that the numerical simulations don't show much of a correlation.
Oh no, the numerical simulations don't show much of a correlation between the kinetic helicity and the electromotive force. So this is looking at the other thing. So if you do a simple two-scale analysis, large scale and eddy scale, the conservation law for the little h, the eddy scale contribution to the magnetic helicity, has a current, has the usual dH dt, and then it has this term, B dotted into the electromotive force, which represents the transfer of magnetic helicity from little h to big H. You're taking the magnetic helicity and putting it on large scales, or you could put it in small scales, but the point is you're transferring it between the scales in the problem. So of course it breaks the conservation law, and then if you have the same law for the large scale magnetic helicity, it has this term but with a minus sign. Now this is really cool actually for two reasons. First of all, if you remember the cartoon of how the dynamo worked, it worked by somehow making all the local little field lines spiral in a systematic way. That's grossly inconsistent with conservation of magnetic helicity. How could you do that? You had nothing, and then suddenly you had something. So this is a cheat in the traditional diagram. There's a mysterious thing going on here. The other thing, though, is that that twisting was necessary for the dynamo. And you see here in this conservation equation, it's the electromotive force that figures in the dynamo in the direction of the magnetic field, which is the part that matters for the dynamo. So what this equation is telling you is that the transfer of magnetic helicity between scales is an essential part of the large-scale dynamo process. Now, if you neglect this side of the equation, this tells you that as you go to a static distribution of magnetic helicity in the eddies, the electromotive force goes to 0. Another way to say this is there's a term in here which is proportional to little h, and it enters into this equation with a positive sign so that you relax to 0 electromotive force. The point at which you turn off the dynamo turns out to be long before the magnetic field reaches equipartition. So this was the original Grushinov and Diamond argument, pointing out that this effect throttled the kinematic dynamo, and it did it when the kinematic dynamo was still young and naive. Kills it in its youth. So it's anti-dynamo theorem. That was 1994. That was really the death knell of traditional mean field dynamo theory. There are still people today who do traditional mean field dynamo theory. The field has had enormous inertia. There's never been a good counter-argument to Grushinov and Diamond. People have just tried to ignore it. Not everybody, but lots of people have tried to ignore it on the assumption that there is a loophole that we will eventually discover. Okay, well, we do see dynamos. So right, we know that's point one. This is a paradox of our own making. It has nothing to do with nature. Nature makes dynamos. We can run numerical simulations that have the ingredients we think are necessary for dynamos, differential rotation and stratification and all the rest of it. And we do see evidence of large-scale dynamo activity. So,
This
Oh, could be.
And you see basically the effect at some level,
Mhm.
before
Right.
your eyes.
But that doesn't mean that that's what runs a dynamo. So, where does alpha suppression come from? It comes from ignoring the right-hand side of that equation. It's saying there's no spontaneous flow of magnetic helicity through a system. Negligibly small. Now, of course, actually magnetic helicity advects just like everything else. And if you build it up in one spot, it will try to diffuse away. These are not big effects. The most important effect is that if you have a differentially rotating fluid, it turns out the magnetic helicity will spontaneously flow in a preferred direction. And it's not a small effect. So if you start out with no magnetic helicity at all, and you turn on differential rotation, you will generate a flux of magnetic helicity, and you will generate regions of positive and negative magnetic helicity. To take a simple everyday example of how you could do something like that, suppose you have a rope with no twistiness, and you put your hand on it, and you rotate your hand. You will drive equal and opposite amounts of helicity in opposite directions, generating a net helicity flux, which will either be to the left or the right, depending on how you rotate. So you do need to break symmetries to make that happen, but it can happen. So how can we get a handle on it? So there's a formal mathematical definition, which is this. I'm sure that this is not particularly enlightening to anyone, but let me just say, here we have the fluctuating part of the electromotive force, the small scale vector potential. This is the electrostatic potential. This is an extra term which arises in a shearing environment. Doesn't add anything qualitatively to this picture, but it is formally there. And of course, it's even a bigger mess than V cross B, and so you might think, well, looks like 0. How can you show it's not 0? You can calculate the leading order terms. And what you're looking for comes from a simple dimensional estimate. And it's going to be of order v squared b squared. And then there's either the shear or the rotation, which will come in. And then you need a second power of the eddy correlation time. So it's computationally going to be uglier than doing the electromotive force, because you need to take 2 time derivatives. And this particular form assumes that shear and rotation are small effects, but of course they can be large. A little bit of symmetry here. This is a pseudo-vector, right? A dot B is a pseudo-scalar. If you reverse the sign of every axis, A dot B switches sign. Multiply, so if we have a vector flux, it becomes a pseudo-vector. And so where this points, it has to point in the direction of a pseudo-vector given by the system. Okay? Pseudo-vector is available. The magnetic field, but the magnetic field can't be a direction for this, because if we reverse the sign of the magnetic field, this flux won't switch sign, but the magnetic field will. The 2 other pseudo-vectors are the local vorticity, due to differential rotation, and the rotation. So for an accretion disk or a galaxy, that's to say that it goes along the axis of the galaxy. For the sun, it can be a bit more complicated. And when you calculate out all the terms, you do in fact get something which is that times a coefficient. Okay, so assuming you know this, then you can estimate the electromotive force, at least the parallel component. This way, you're just crossing out dH/dt, assuming that that's hit saturation. And what you see is the electromotive force is proportional to this divergence of this flux, and it's inversely proportional to the magnetic field strength, which immediately tells you that when the field is weak, it grows rapidly, and when it's strong, it grows slowly. So the way you'd expect a dynamo to go is not that it grows exponentially, it's that it will rapidly grow, and then it will slow down, and eventually that will be balanced by dissipative effects or buoyant losses or something.
So you're not including your large-scale meridian flux?
No, there's a condition under which you can ignore it. It's pretty generous. I'm not going to worry about it. If I'm making a detailed model of what the sun does, I definitely will worry about it. But this is just a schematic picture of how dynamos work in general, and I'm not going to worry about it. Okay, is this a self-consistent picture? Because it's pretty outrageous. If you think about it, what I've done here is I've ignored the thing that's supposed to drive the dynamo, and I've picked a different effect entirely and put all the onus for driving the dynamo on that. So you can ask if this is self-consistent. One simple way to do this is take the magnetic helicity flux. I know about what it is. Ask how long it takes for that flux to accumulate to such a level that the local value of the current helicity is bigger than the local value of the kinetic helicity. The time scale for that happening is 1 eddy turnover time. Since 1 eddy turnover time is the shortest time we're going to worry about in this model, that's another way of saying the kinematic dynamo in general does not exist in astrophysical objects. The kinetic helicity is always overwhelmed by this effect. Now, honestly, when the large-scale field is very weak, you can't set dH dt equal to 0. The magnetic helicity can accumulate locally without being immediately translated into a dynamo effect. So the early evolution is a bit different, but that's okay. It doesn't have a huge impact. So what does this mean for something like the solar dynamo? You know, the detailed answer is not available because no one has included this effect in a detailed model of the solar dynamo. And I'm gearing up to try this. I'm not any kind of expert on solar dynamo models, but it seems straightforward enough. He said famous last words, I guess. But the point is that there's only one group that even includes magnetic helicity conservation in their solar dynamo models. And they impose it by, well, basically they put it in by fiat, and then they add a magnetic helicity flux, which is just due to the fusion of magnetic helicity and its movement through meridional flow. So they're leaving out the most important term. By the way, they get great models for sunspots, the sunspot cycle. So their model is also slightly more physically realistic than the others, and just as good in terms of what it produces.
Is there any trickiness on the boundary? You're setting boundary conditions for the magnetic helicity flux?
One presumes that the magnetic helicity at the boundary leaves at the same rate as the magnetic field energy. I suppose that could be wrong, but that seems like the obvious choice. We have tried this in a box, not in a star, but just, a periodic box, drive a large-scale shear in the box, ask what happens to the magnetic field, and we drive a dynamo whose growth rate depends on the local accumulations of magnetic helicity, whose saturation value is actually much more than the local turbulent energy density. But that's because of the parameters we chose. It looks like a vindication of our model in a box. Qualitatively, what would we expect to happen? Well, in a box, you have a growth rate which is decreasing and a turbulent dissipation which is mixing the field. And at some point, you're going to hit saturation between the two. This gives you an estimate of the Alfvén speed at saturation. And it's got, well, for dimensional reasons, it's got the density to the 1/2, but then it's got the size of the box times the shear. So this is a generic limit for a magnetic field in a box. And the work we did together, Dmitry Shapovalov and I, we chose L and S so that this product was actually greater than the root mean square turbulent velocity. And this is what it went to. Now, in real objects, you have buoyant losses of magnetic field, regions which are have a magnetic field energy density which is greater than the surroundings because of pressure equilibration. They also weigh less, they float. So if you have a turbulent medium and the magnetic field fluctuates, the regions with more magnetic field will move upward for 1 eddy turnover time. You get a net drift out of the system. When you put in the buoyant losses, you get that the magnetic field instead scales as a pressure scale height times the shear. which is more physically realistic for stars.
So going back to the numerical simulation, you compared this LS to B turbulent squared.
Yeah.
You were just driving a shear, or were
Yeah.
you steering a shear?
We drove a shear and we drove local turbulence. So these were separate knobs that we could turn.
And the shear wasn't enough itself to give you the turbulence.
No, but we had to play with that a little bit because well, I don't think that the project I did with Dmitry was the cleanest possible way of putting in shear, and I have another project approaching completion, which we do it in a more systematic shearing box way in order to avoid some of the complications. Okay, so all of this is assuming that the turbulence is close to being locally isotropic. It's not strongly affected by the shear and rotation. The large-scale magnetic field is weak. You might ask, how does any of this affect the answer? Well, if you put in a strong background field and you go through the equations, this mean square fluctuating magnetic field, you get a separate set of terms which depend on the background field, but instead of this, you have this. That is the parallel component of the turbulent eddy wave vector dotted into the magnetic field squared and then divided by the total wave number squared. Imagine you keep turning up the background magnetic field and you have some driving mechanism which imposes a rate. Okay? The magnetic field lines eventually are stiff to the background perturbations, which means that they don't bend easily, and the component of the wave vector along that direction starts becoming smaller and smaller. So this product here can never be greater than roughly the turbulent driving rate for convection, the convection rate. So this separate term saturates when it's about equal to the term that you get just from the background turbulence. It never dominates. So the background field doesn't produce a qualitative change. Suppose rotation is fast. The sun, it's not fast, but some stars, it's fast. The Earth, it's fast, right? Well, so you have a very large rotation rate. If you look at the equations for the dynamical evolution of the eddies, what you find is that the expression for magnetic helicity flux ends up being multiplied by the vertical wave number squared over the total wave number squared. This is the well-known effect. You get that from the magnetic helicity expression. If you ask what that means, it's well known that in rapidly rotating turbulence, the vertical wave number starts to become small as the rotation rate increases. That is, you start getting columns within the rapidly rotating fluid. And so the net effect is that the magnetic helicity may be proportional to the rotation, but this factor is proportional to 1 over the rotation squared. So as you increase the rotation rate to small Rossby numbers, strongly rotationally dominated, the magnetic helicity becomes less important. Magnetic helicity flux becomes smaller, going as 1 over the rotation rate. So in a real system, that means that the dynamo has to be dominated by the shear term at that point. So what if the shear is strong? When you have very strong shear, you stretch the turbulence along the azimuthal direction. And the turbulent eddies become narrower and narrower radially, and the radial velocities and radial magnetic fields become smaller and smaller compared to their mean square values. So the net effect is, on the magnetic helicity flux, is that once again you get a prefactor which turns everything off at 1 over the shear squared. If you look in detail at all the terms, there's no single factor, but you either have a 1 over radial wave number squared coming into the expression, or really it's the other components of the wave vector squared over the total wave vector squared, or you have b sub r squared, or you have v sub r squared. But all the terms are affected by at least one of these things. So rapid shear turns down the magnetic helicity flux. The net effect is the magnetic helicity flux goes as 1 over the shear. The other half of the dynamo cycle, the stretching of the field lines, goes as the shear. So the whole thing asymptotes to being insensitive to the shear. You get a dynamo growth rate which does not depend on the shear. And when you replay the argument about the saturation, balancing buoyant losses against this reduced magnetic helicity flux, you get that the toroidal magnetic field, which is the dominant component, now depends on the vertical scale height, pressure scale height, and the eddy turnover rate. Well, if you compare this to convectively driven turbulence, what you see is that this is in equipartition with the turbulence, which is, when you think about it, quite odd, because the way the energy is flowing into the magnetic field is almost entirely from the large-scale shear. Nevertheless, the local turbulence controls its final amplitude. So, for a star, can we learn anything from this very schematic treatment? Well, obviously I can't tell you anything about magnetic cycles like the sun's 11-year cycle, because that relies on a detailed dynamical analysis. But look at what this says. First of all, crudely speaking, the magnetic energy losses from the system are the saturation velocity, saturation magnetic field squared times the buoyant loss rate. And that should be correlated with the X-ray luminosity of a star. So you can just ask, what does this tell you? This tells you that the X-ray luminosity of a star should be proportional to the convective flux of energy within the star, because the vertical convective velocity is faster than but scales with the buoyant escape velocity, and the energy density of the magnetic field is the same as the turbulent energy density in the convection. So in a rapidly rotating star, we should get a graph like this. I am not responsible for this graph, except, I listened to the author give a talk, and then I stole it from his paper. But this is a compilation of different sources put together by Reiners. And this is X-ray luminosity. No, excuse me. This is actually a measure of the magnetic flux density. I put these in the wrong order. Here's the X-ray luminosity versus Rossby number, which is 1 over omega tau. So these are the fast rotators. These are the slow rotators. Here you see this is going up as the rotation rate squared, and then this is leveling off. Okay. This is a somewhat more difficult measurement. It's the magnetic flux in star spots, so a measure of the internal strength of the star's field versus Rossby number. And it shows here a linear rise with rotation rate and then an asymptotic state. So the two graphs are independent measures of the same thing. And they're both consistent with the predictions of this dynamo model. You will note that the turnover here and in the other graph is not at a Rossby number of 1, but it's something that's like a tenth or maybe a tiny bit smaller. But of course, the turnoff in our model is a combination of the rotation turns off a little bit of the flux, and then the shear turns off the rest, and the shear is some fraction of the rotation depending on the system. So that's a completely reasonable displacement. If it went in the other direction, if it were 1 or bigger, that would be very odd. Okay, so we can explain the strength of stellar magnetic fields as a function of their rotation rate, which is really, it's very exciting. Do you ever have the feeling when you work on a theory for long enough and someone proposes an experimental test that instead of being elated, you get this sick feeling in the pit of your stomach? Well, it all worked out in this case, so it was good. But I was quite far along in this project before it ever occurred to me that it was making a prediction. Okay. What else can you say from this theory? Well, presumably the same kind of dynamo effect is supposed to be working in the galaxy or in an accretion disk. Now, galaxies are particularly interesting because absent some very strange symmetry breaking effects in the early universe, they start out essentially unmagnetized. And yet, we always see them magnetized. So, how do we tell a picture in which we make the transition between the two quickly and efficiently? Well, okay, you make a disk of a galaxy. Now, it doesn't start out full-blown like the Milky Way disk, but let's ignore that for a second and just imagine we're talking about the Milky Way to begin with. They start out unmagnetized, but they're turbulent. So, of course, the small-scale dynamo is the first thing that happens, regardless of the cosmological seed field supplied. The energy density of the magnetic field in the galactic disk will, in 20 or so eddy turnover times, be comparable to the energy density of the turbulence, but not very organized. On the other hand, in addition to coming to equipartition with a typical scale like the eddies, there's going to be a long wavelength tail, which takes a bit longer to establish itself, basically a dissipation time, and it evolves toward a Poisson distribution. And that's just the individual eddies contributing random electric fields on larger scales. And if you let this process go to completion, it takes something like a galactic rotation for parameters like the Milky Way, a full period of galactic rotation. Now, the rotation of the galaxy is, of course, strongly differential. So you're shearing the large-scale magnetic fields as you're making them. And if you consider a domain which is like an annulus of a disk, that shearing will quickly give you a large-scale toroidal field with a strength of about 1/10 of a microgauss. That's still, a factor of 30 or so below where you're headed. But if you compare that to cosmological discussions of starting from a weak seed field and directly generating a large-scale field, you see that a factor of 30 is a lot easier to explain than a factor of 10 to the 14th or so. So this is good. But the other thing is that as soon as the eddies are magnetized, as soon as the small-scale dynamo has done its work, then the turbulence is generating a flow of magnetic helicity, segregating magnetic helicity between the northern and southern regions of the galactic disk. And that drives a large-scale dynamo. At first, it just passively accumulates, but then you get enough of a large-scale field that will couple to this, and it will drain the small-scale magnetic helicity into the large-scale magnetic field. And you get a growth rate which is super exponential, but slows down toward the end. And that takes, it maybe adds another full rotation, one full rotation of the galaxy to your growth, but not more than that. You actually start this coupling before the long wavelength tail is finished growing. So, I don't know, 2 or 3 rotations of the galaxy will do it. It may stop a bit. You just assume you have a fully formed galaxy and not quiescent. The disk has to be turbulent for this explanation to work. But yeah. Now, this is not how galaxies form. Right? You make little bits of galaxies and you mash them together, and the whole story is more complicated. You start from smaller units. Of course, that's good, because for smaller units, it should go faster. Anyhow, within a few rotation times, you're at a stage where the magnetic field is not just in equipartition with the turbulence, but it's organized on annular domains. So if you're trying to measure the magnetization of a galaxy from a line of sight through the disk, you will see an organized magnetic field. Now, if you have multiple lines of sight through the disk, you might notice that there's more than one magnetic domain. Well, I can live with that. So, to summarize, traditional mean field dynamo theory can do a pretty good job of modeling the solar magnetic cycle. It doesn't naturally generalize to explain, well, very much else, and does not correspond to the dynamo we see in direct simulations. This version, I think, shows a better connection between basic physics and the dynamo effect, and also has the virtue of naturally predicting the dependence of stellar magnetic fields on rotation.
What are the precise equations here involved? I mean, in the mean field equation, you have the, alpha b as a source, or the axis of the toroidal vector.
I'm using the full dynamic equations minus viscosity and resistivity to estimate the magnetic helicity flux.
Yeah.
Then I'm using the magnetic helicity flux to estimate little v cross little b.
Okay. And you put that in the induction.
And then I'm putting that in the induction equation.
But that's the step I'm a little confused about. Because, okay. How precise, I mean, is there an unambiguous way of doing mathematics?
For a full mathematical treatment of this, of course, I'm just doing a sort of, I'm filtering at a single scale and saying,
What I'm asking is there an analog of equal equations which the occlusions and condenseness are well defined?
oh yeah, I mean, you can define the analog of the mean field equations with any number of scale filters and trace the transfer of structure from small scales to large scales across
No, I mean,
any set of scales.
your magnetic velocity flux estimate of V cross B, is there a similarly simple prescription, a clean local prescription for V cross B that you can exact? Maybe you flashed that and I missed that.
Well, basically, I'm taking the conservation equation for little h, for the small scale the eddy scale contribution to the average magnetic helicity, and I'm dropping the dH/dt term,
Yeah.
although I can keep it and make a slightly more complicated set of
Well, we
equations.
go over this after that. So-
Okay. I don't normally make a point of this, but someone raised this question yesterday, so I thought I'd address it directly. If you could measure the eddy scale magnetic helicity and the large scale magnetic helicity in the same region of space, traditional mean field dynamo says that they should be of opposite signs. This model says they're the same sign. And traditional mean field dynamo theory would say that they probably are comparable. This would say the large scale magnetic helicity is much bigger than the small scale magnetic helicity because that's where all the magnetic helicity ends up.
So physically, there's this whole idea of cell logis that you take them as a large scale magnetic field, you twist it and fold it, and then there's a compensating small scale twist on the field that results from that exponentiation of that process. And this is exactly the cancellation you're talking about in the mean field equations.
Yes. And I'm saying we get around this in this model by moving the small scale twistiness around.
Yeah. Okay, so, the thing that convinced me long ago, that basic idea of combination of an omega effect and alpha effect has physical validity, was what you see at the surface of the sun. The sun has a surface. Okay, so let's go through the following thought experiment. I start off with a photomagnetic field, and I simplify a shear at the base of the question, no problem. Right? And then I let those amplified photomagnetic field rise point to the surface, okay, and then flow originally back. Okay. Now, can you? So in this process, in order to get the opposite sign of the correlation of the helicities, do you have to have some specifics? Loss of small scale twist at the surface?
No, you don't have to lose magnetic helicity anywhere. I mean, like I said, I can simulate this in a box.
So it's a flux from where to where then of the magnetic helicity?
Well, a flux from one magnetic domain to its neighbor.
You mean from one hemisphere to the other?
Sure, for example.
Is that really realistically how it would happen?
Sure. In the sun, it would happen toward the base of the convective zone where the convective cells are large, and it would it'd be driven by the shear and the rotation in that part of the sun. So it would couple the two hemispheres together.
Okay. So you can avoid the surface playing a role if you couple the two hemispheres.
Yeah. And in fact, if you do a crude estimate of where the magnetic helicity flux is big in the sun, you find that it's big deep in the sun, and the effects on the surface The magnetic helicity flux near the surface is relatively small.
It's just because the scale height's bigger, you're saying?
I'm saying, yeah, because the scale height is bigger down toward the bottom. That's basically what's driving it.
This is getting too for the experts.
Yes, I'm sorry. Anyhow, yes, that's the end of the talk. We can trail off into an argument with interested parties.
Maybe one last question for you. If there is any burning questions.
I just want to go away with a clear understanding of this one slide, which is this observed saturation of the dynamo, which first is going up with shear and then saturates. So what's
Well, you don't actually measure the shear, right? You measure the rotation. But yes, it goes up with as rotation increases.
Is there another way of which is like to understand this?
Okay. Yeah, the simple way of saying it is the dynamo cycle has two pieces to it, right? There's the generation of colloidal field from toroidal field, which has got this complicated turbulence and twisting part to it. And then there's just the simple shear of the colloidal field into the radial field. That second step depends directly on the shear, and indirectly, we think, therefore, on the rotation. So it's more efficient as you turn that up. The first part, in this model, it starts out similarly. You know, if there's no rotation, then there's no preferred direction for any flow, and the flow is zero. So in beginning, the magnetic helicity flux is proportional to the rotation. So you have two powers of rotation. It's the geometric mean of the two which matter. So the growth rate is proportional to the rotation. Okay, now you start to build up to the point where the rotation and the shear have a serious dynamical effect on the turbulence. Well, magnetic helicity is this three-dimensional twisting. Okay, and then you have to take the twists and move them. So the underlying physical reason why things become less efficient at that point is because strong shear and rotation flatten the eddies. And so the eddies are no longer extended equally in all directions, and three-dimensional twisting is harder to transport. The effect then switches from being something that rises linearly with the rotation and shear to something that falls as 1 over the rotation or shear. So now you have one piece that increases steadily with shear and its effectiveness, and another piece which decreases linearly, and the geometric mean of the two is nothing. It's asymptoting to a constant.
It's correction to the convection, correction to the turbulence.
Yes.